In this session, we'll consider the derivation of the discrete Fourier transform from the discrete time Fourier transform. So before going for the discrete Fourier transform, let us see why do we need the different kinds of transforms. So already we have seen the different types of signals. One is called as the continuous time signal, other one is the discrete time signal, and similarly the continuous time as well as the discrete time. So what we'll do is, so if your signal is a continuous time signal, we are going to apply for the Fourier transform you're going to apply where it will be equal to the in the time domain the signal is continuous, and in the frequency domain also the signal is continuous. Suppose if the signal is the discrete time signal, we are going to apply the discrete time Fourier transform you're going to apply. We are going to apply the discrete time that is called as a DTFT you're going to apply. So where the signal will be in the frequency range also it's a continuous one. In the frequency domain it is continuous, in the time domain it will be the discrete one will be there. So one of the drawback of the discrete time Fourier transform is in the frequency domain the signal is not discrete one, but it's a continuous one will be there. So for the drawback of this one is because for the digital signal process, so since it is operating on the digital signals, so it can't perform the frequency analysis of the signals. It is not possible to perform because since the signal will be in the analog in nature, or it will be continuous with respect to the frequency. So in order to overcome that one, what we are going to do is we are going to consider the discrete time Fourier transform you are going to consider. And for that one, we are going to perform the sampling in the frequency domain, and we are going to obtain a new formula which is called as the discrete Fourier transform, in which the time domain also discrete, frequency domain also discrete is there. That's why the name it is called as the discrete Fourier transform. So what shall we do is let us derive that formula. Let us derive now. So we'll consider the derivation of that formula. So here what will be done is I'm going to consider the non-periodic signal will be considered. Non-periodic signal we are going to consider. We are going to sample that one and will be further processed. We are going to sample that one. We are going to further process that one. So what will be done is, so the DTFT of the discrete time signal. So the DTFT of the discrete time signal, which is called as X of n. X of n is the discrete time signal, in which it is a non-periodic signal. Non-periodic signal. So if you're going to apply the Fourier transform of the discrete time non-periodic signal, you are going to get the discrete time Fourier transform you're going to get. So that is given by the discrete Fourier transform is given by x of e to the power of j omega n. So x of e to the power of j omega. So this is the thing, but the formula is summation n is equal to minus infinity to the plus infinity x of n into e to the power of minus j omega n. So this one can also be written as x of j omega we can write. So these are the different notations of different way of representing the signal in the frequency domain. So here the signal x of n is discrete in nature, but it's a aperiodic signal or it's a non-periodic signal. So this is the signal x of n. And when you take the discrete time Fourier transform of this one, when you take the discrete Fourier transform of this one, so it will become the x of e to the power of j omega. We are going to, it's a periodic spectrum you're going to get here. So this is x of e to the power of j omega. So this is with respect to the omega axis. It is continuous in the frequency domain, but here it's discrete in the time domain. So that's the advantage of the DTFT. So in the time domain, it is non-periodic, but in the frequency domain, it is periodic with the period equal to the 0 to 2 pi. So what you are going to do is, since in order to obtain the discrete Fourier transform, you are going to perform the sampling of the signals you are going to perform here. So what will be done is we are going to take the samples in the frequency domain. You are going to perform the sampling we are going to perform here like this. We are going to take the n number of samples you are going to take in the interval 0 to the 2 pi. We are going to consider the n number of sample. So the first sample is 0th one, the next one is 1, 2, and also this one will be equal to the n minus 1 will be there. N minus 1 sample you are going to consider. That is within the range from 0 is less than omega is less than or equal to 2 pi. We are going to consider the n number of samples we are going to perform, n number of samples you are going to take, so that since the period is 0 to 2 pi, the n number of samples you are going to consider, the spacing between the sample, each sample will be equal to the, so delta omega is the thing, but it's a spacing between the each individual sample. We are going to call it as a delta omega. So this is delta omega we can call. So that is the thing, but it will be equal to the, since we are considering 2 pi divided by n samples you are going to consider here. Okay, so now in order to obtain the discrete Fourier transform from this one, So we need to find out the Fourier transform of the discrete Fourier transform of any one of the kth sample you're going to consider. For example, assume that, so since we have a number of samples between the range, so I can take k is one of the variable which can represent the one sample among the n number of samples here. One sample among the n number of samples, the k is going to represent here. So if I want to find out the discrete Fourier transform of the particular kth sample, then I can substitute omega is equal to the, so 2 pi divided by n is the spacing between each sample, and k denotes the spacing between the which sample will be there. For example, if I substitute k is equal to 0, then I am going to get the 0th sample I will get. If I substitute k is equal to 1, I am going to get the first sample, k is equal to second sample, and k is equal to n minus 1, I am going to get the DFT of the n sample you're going to get. So what will be done is, you're going to obtain the formula with the mathematical manipulation. So if I'm going to substitute k, where x of j omega or e to the power of j omega, if I'm going to substitute omega is equal to the 2 pi k divided by n, so I can able to obtain the DFT formula I can able to obtain from this one. So how do we obtain? So here we have the formula for this one. So that is, I'm going to manipulate the formula, that is x of e to the power of j omega. We have this formula, summation n can take the value minus infinity to plus infinity, and this is x of n. In place of omega, I'm going to substitute e to the power of minus j. 2 pi k divided by n we are going to substitute, into n already is there. So this is a formula we are going to substitute. So this one we are going to call it as the sequence x of k we are going to call. So here, since it is taking infinity to minus infinity to plus infinity, we are going to manipulate this one, and we are going to make the signal x of n is within the finite duration sequence. So with mathematical manipulation, we can able to obtain, let us assume the signal x of n is the periodic. So we can able to obtain by truncating to the 0 to the n minus 1, we can able to obtain the DFT formula like this we can able to obtain. So e to the power of minus j 2 pi k n divided by n. So this is the formula for the DFT we can be able to obtain, where x of n is going to be assumed to be the periodic sequence with the period equal to the capital N. It's a finite length sequence with the value equal to the duration of this sequence is equal to the capital N. So similarly, by using the Fourier series formula, so we can able to obtain the inverse DFT, that is x of n we can able to obtain. So that x of n is given by, so 1 by n summation k is equal to 0 to the n minus 1 x of k into e to the power of plus j 2 pi k n divided by n. So this is called as the inverse DFT formula we can call inverse DFT, and this is called as the DFT formula, the discrete Fourier transform formula we are going to consider. So by using this form, the DFT pairs we are going to form. So this one can be represented as a pair of discrete Fourier transform like this. So it is the x of k. So now for this sequence, so since we are going to represent in the exponential form, we are going to introduce the nth factor unity we are going to call, that is as a twiddle factor we are going to introduce. So twiddle factor we are going to consider, that is called as the omega n we can call. So where omega n is nothing but e to the power of minus j 2 pi divided by capital N. So this is called as the nth root of unity. It is also called as a twiddle factor we are going to call. So this is called as a nth root of unity. It is also called as the twiddle factor we are going to call. So this is the by introduction of this twiddle factor in place of here, in place of in the DFT formula. So in the DFT formula here, e to the power of minus j 2 pi divided by capital N can be represented as a omega n twiddle factor. The remaining terms are nothing but k and n. So with replacing those terms, we can able to obtain the x of k. So this x of k is equal to summation n is equal to 0 to the n minus 1 x of n into omega n to the power of k into n will get. So here k can take the value from 0 to the n minus 1 it will take. So similarly in the IDFT formula, same way we can do replace here, that is in the IDFT formula. So x of n is equal to 1 by n summation k is equal to 0 to the n minus 1 x of k into omega n to the power of minus kn. So here n can take the value from 0 to the n minus 1. So this is the pair of DFT formula pairs where we can use in order to calculate in order to solve the problems, whether it may be the endpoint DFT it may be the fixed duration sequences we can find out. And this formula will be helpful for the computers where in the time domain also discrete, in the frequency domain also it is discrete. So both the domains it will be discrete, so that the frequency analysis of the signal can be easily performed by the digital computers or the DSP process, and we can able to perform the frequency analysis of the signal. So where it will be useful in the design of the filters, it may be low pass, high pass, or any filters in order to remove the noise. So these are the concepts. So in the next session, we'll look into the properties of the Twiddle factor. We'll see here some the two properties are the one is called as the periodicity property, other one is the symmetry property, which are very important. So we'll look into that property.